Now in chapter 3, current electricity. In this chapter we will learn about electric current and the concept of drift velocity, Ohm's law, electrical resistances, a cell, Kirchhoff's laws, then Wheatstone bridge, a meter bridge without the derivation, and potentiometer principle in its application, again without the derivation. So we'll start with the first topic, which is electric current. Electric current. Now the flow of electrons in a conductor constitute a current. We have learned about a conductor in chapter 2. We know that conductors, they are materials which conduct electricity. And inside a conductor, there are free electrons and positive ions. And these free electrons, they are free to move inside a conductor, and the positive ions, they remained at one fixed place. And the flow of these free electrons inside a conductor upon application of an electric field across the two ends of the conductor constitute an electric current. And your electric current may be defined as the rate of flow of electric charge through any section of a wire. It is denoted by I, hence I is equal to total charge flowing through the section of the wire divided by the time taken, and that is equal to Q by T. Q is the charge flowing in time T through any section of the wire. Now here we can see from this formula that the current depends upon the total charge, which is the electrons. So if there are more electrons inside the conductor, the current will be more. And it also depends upon the time taken for the charges to flow through the section of the wire. If the flow of electrons is fast, if the electrons moves fast from one end of the conductor to another end of the conductor, then the electric current will be large. So here, if the time taken is small, then the current will also be large. From this formula, I is equal to Q by T. Now this formula applies for direct current. That is, if we connect the two ends of the conductor to a direct source, that is to a DC battery. But if we connect this conductor to an alternating current source, then the formula that we'll have to use is this instantaneous current. That is, if charge dq flows through a wire in small time dt, then I is equal to ddt of q. So we'll have to take the derivative of this charge flowing through the conductor in the small time interval, and this will give us the instantaneous current, that is the current at any instant of time. So here we have two formula for electric current. One is I is equal to Q by T. You can use this for direct current. And another one is I is equal to ddt of Q. You can use this formula to calculate current, alternating current. Now, if N is the number of electrons flowing through any section of a wire in time T, then I is equal to NE. Now here E is the elementary charge and is equal to 1.6 into 10 to the power minus 19 coulomb. And N is the number of electrons. So using quantization condition from chapter 1, your Q is equal to NE. Here we are not writing positive or negative because electric current is a scalar quantity and is always positive. And from the formula, the SI unit of current is ampere. And again from the formula, ampere is equal to 1 coulomb per second. The SI unit of charge is coulomb and the SI unit of time is second. So here we have 1 ampere is equal to 1 coulomb per second. So here we can define the 1 ampere. The current 1 ampere, the current through a wire is called 1 ampere if 1 coulomb of charge flows through any section of the wire in 1 second. So that is the definition of 1 ampere. Now we come to the concept of drift velocity. Now in conductors, the free electrons are always in random motion, and this random motion is due to the thermal energy of the conductor. The velocity by which free electrons move randomly in the conductor is termed as its thermal velocity. So the electrons inside this conductors, they are in motion because of the temperature of the conductor. Now, even at room temperature, the electrons have energy, so that they will be in random motion. Now, if we increase the temperature of the conductor, then what will happen is that the electrons will move faster inside the conductor. And this concept will be used in temperature dependence of resistance. So you need to remember that upon increasing the temperature of the conductor, the free electrons inside the conductor, they move faster. Now, due to their random motion, the free electrons keeps on suffering collisions with the positive ions in the conductor so frequently that the net flow of electrons in any one direction is zero. Now we know that inside the conductor there are free electrons as well as positive ions which stays at one place. Now the electrons, they always collide with these positive ions, and the collision is very frequent. It happens frequently. Hence, the net flow of electrons into any one direction is zero. So it means that there's no flow of electron in one direction. So the current is zero. Remember, the flow of electrons in any particular direction will constitute a current. So here, the net flow of current in any one particular direction is zero. So the current is also zero. In other words, the average thermal velocity is zero. So if we take the thermal velocity, the average thermal velocity, add all the thermal velocity of the individual free electrons, that is u1 plus u2 plus u3 plus dot un, where n is the number of free electrons, and divided by the number of free electrons n. This is known as the average thermal velocity, and it is equal to 0. So this is because of the random, the collision in which the free electrons is having with the positive ions, and that there's no net flow of electrons in any one particular direction. So this happens if you don't apply any electric field. However, when an electric field E is applied across the ends of the conductor by supplying a potential difference V between the two ends of the conductor, then we know that from chapter 1, any charge under the influence of electric field will experience a force. So in this case also, the electrons which is inside the conductor, they will experience a force, and that force is equal to minus E vector. Now mind, this E is the elementary charge and E vector is the electric field between the two ends of the conductor. Now from this formula we know that the force, since electrons are negatively charged, they will be attracted towards the positive end of the conductor, and electric field will be in the opposite direction, that is from positive to negative. Hence this formula shows that the force experienced by the free electrons is opposite to the direction of the electric field. Now if m is the mass of the electron, then using Newton's second law of motion, force is equal to mass into acceleration. Hence your acceleration will be equal to minus EE divided by m. So under the effect of electric field, the electrons will accelerate and acquires velocity. But this will happen for only a very short period of time, because we know that there are positive ions inside the conductor. So when electron accelerates, it only happens for a very short period of time, and then it collides with the positive ion. So here the electron accelerate, okay, it gets scattered on collision with the positive ion. So this acceleration happens only for a very short period of time. And the short period of time for which a free electron accelerates before it collides with the positive ion in the conductor is called the relaxation time. And this relaxation time is very small. So here, if an electron with terminal velocity u1 accelerates for a short period of time tau1, then it will attain a velocity. This is from the equation of motion. v1 is equal to u1 plus a tau1. Okay, this formula is from the equation of one of the equation of motion. Here u1 is the initial velocity, a is the acceleration, tau1 is the time in which the electron accelerates, and v1 is the final velocity it attains. Similarly, other electrons will attain velocity v2, v3, vn, where n is the number of free electrons. Now we come to the definition of drift velocity. So upon knowing these velocity of each electrons under the influence of the electric field, the drift velocity can be defined, and the drift velocity is defined as the average velocity with which free electrons gets drifted under the influence of an external electric field applied across the two ends of the conductor. So drift velocity can be denoted by Vd and is equal to the average, that is the sum of the velocities of all these individual electrons, which is v1 plus v2 plus v3 plus vn. Okay, n is the number of free electrons, then divided by the number of free electrons, that will get the average velocity. And this average velocity under the influence of electric field is called the drift velocity. And from the formula above, your v1 is equal to u1 plus a tau1, v2 is equal to u2 plus a tau2, v3 is equal to u3 plus a tau3, vn is equal to un plus a tau n. So you put it in this equation, what we'll get is this formula. Then what we do is we take u in one group, okay, the thermal velocity in one group, that is u1 plus u2 plus u3 plus dot 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 plus un divided by n. This is in one group. Then the tau1, tau2, tau3, tau n in another group. So we have plus a, which is common, same for all the free electrons. Then tau1 plus tau2 plus dot dot plus tau n divided by n. And since we know this average terminal velocity is 0, so here we have Vd to be equal to a tau, and this tau is known as the average relaxation time. And a, we have seen this formula. Your a is equal to minus ee divided by m tau. So this the above expression, that is Vd is equal to minus ee divided by m tau, is the expression for the drift velocity. So here you need to remember this expression, and also remember that only under the influence of the external applied electric field that the electrons get drifted inside the conductor, and that the drift velocity is opposite to the applied electric field. So from equation 1 we can find that Vd is equal to minus, which indicates that the drift velocity is opposite to that of the electric field E vector. Now we come to the next topic, which is relation between drift velocity and electric current. So we have learned about an electric current and drift velocity. So we will relate these two quantity. Now in the diagram we have a conductor of length L and area of cross section A, and this conductor is connected to a battery of potential V between its two ends. and one end is positive and the other end is negative, and there's an electric field across the two ends of the conductor. Hence, the free electrons inside the conductor will be drifted towards the positive end of the conductor with a drift velocity Vd. Now, from your definition of electric current, we have defined electric current to be the rate of flow of charge, and here in equation 1 we have I is equal to Q by T. Q is the total charge of the total charge inside the conductor, and T is the time in which the charges flows inside the conductor. Now, if N, we define a quantity N to be an electron density, and this electron density is the total number of electrons in the conductor per unit volume of the conductor, and it is equal to N, capital N, which is the total number of free electrons inside the conductor, divided by A into L, which is the volume of the conductor. And this capital N, the total number of free electrons, is equal to NaL. This small n is the electron density. Hence, from quantization of charge, we have Q, the total charge in the conductor, is equal to the total number of free electrons N, capital N, into E, the elementary charge. And using N is equal to NaL, your Q is equal to NaLe. Now let Vd be the drift velocity. Then the time taken for the free electrons to cross the length of the conductor is given by this formula. T is equal to L by Vd. Now this comes from the definition of velocity. Velocity is equal to, or speed is equal to, length divided by time. Hence the time is equal to length divided by the velocity Vd. And putting the value of this T and Q in the equation 1, we have I to be equal to NaLe divided by L by Vd. And you cancel L and L. What you left is with NaVdE. So this is the relation between the current I and the drift velocity Vd. And here we can see that the current depends upon the electron density, the cross-section, the area cross-section A, the drift velocity, and the elementary charge E. So you need to remember this relation. We shall use this relation to derive or to prove Ohm's law. So remember, keep this in mind. I is equal to NaVdE. N is the electron density, not the number of electrons in the conductor. A is the area cross-section of the conductor. Vd is the drift velocity, and E is the elementary charge. Then we come to another definition, which is electron mobility. Now, electron mobility may be defined as the drift velocity acquired per unit strength of the applied electric field. It is denoted by mu, and this mu is equal to Vd divided by E. So the drift velocity per unit strength of the electric field, and Vd, just the magnitude, is equal to E tau divided by m. So if you cancel E and E, what we will get is mu to be equal to small e, then tau divided by m. And substituting Vd is equal to mu E in the relation of drift velocity and current, I is equal to NaVdE, we get I to be equal to Na mu E. So this is another relation between the current and the electron mobility. So you just need to remember the definition and the formulas here.